Greetings and welcome. This is Dr. BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be learning about the linear impulse and momentum and conservation of momentum. The outcome of today's topic would be recall the concept of conservation of momentum for knowing the velocities and momentum before and after collision of bodies. The topic covered would be linear impulse and momentum, conservation of momentum. The topic learning outcome is understand the concepts of impulse and momentum and apply these in collision of bodies. First, let us understand what the impulse means. Impulse momentum method is useful for solving problems involving force, time and velocity. As we have seen in the previous case of work energy method, where the problems will be involving forces and distances, then the moments or velocities are being given, then we will be identifying the work energy method for solving the problems. In this impulse momentum method, it will be used for solving the problems which involves force, time and velocity also. The term impulse is defined as the product of force and time. And the momentum, we already have seen, it would be the product of mass and velocity. So how this impulse momentum equation would look like and how we will be identifying the equation for solving the problems, that we are going to see. First, let us find what the linear impulse and momentum equation would be. Let us consider there is a body on which number of forces are acting in different directions. Let us say this is force 1 and this is force 2 and this is force 3. And these forces are acting in different directions and at different places. If at all these three forces which are acting are replaced with a single force, let us say that force is acting in this direction and that is the resultant which gives the end result of all the forces that are acting in the system, that is F1, F2 and F3. If we replace the forces F1, F2 and F3 and place a single force, that is the resultant which gives the effect on the body, the same effect which all the forces F1, F2, F3 will be giving. Now, this resultant R is considered for the derivation which we are doing in the impulse momentum equation. So, the derivation is like this. If R is the resultant force acting on a body of mass m, so the body which we have considered is having mass m. Then from Newton's second law, we know that from Newton's second law, we can say R is equal to ma. That means force is equal to product of mass and acceleration. We have replaced this force, whichever force that are being acted in the system on a body, we have replaced all the forces with the resultant. So we are considering directly the resultant, and the value or magnitude of the resultant is given as the product of mass and acceleration. This acceleration A, which we are considering here, is the acceleration that is achieved by the object or body when all the forces that are acting in the system are implied. So when forces here, as the example we have taken the forces F1, F2 and F3, when these three forces are acting in the system, let us say the body has achieved an acceleration of A. That is the acceleration A that we are considering here. But we already know that acceleration A is given as the rate of change of velocity. That means we can directly imply the equation A as dv by dt, where dv is the change in velocity and t is change in time. So if we replace this given R is equal to ma in the R is equal to ma equation, if we replace the acceleration term A with this dv by dt, then we will be obtaining the equation as R is equal to mdv by dt. Here what we are doing, we are replacing the acceleration with dv by dt. So now again in the next step simplified, how we have achieved this equation is, we are changing this denominator term to left hand side. So we have obtained R into dt is equal to this m into dv. So as a end result, we can obtain R into dt is equal to m into dv. Now we are integrating when time t is equal to 0 to t and velocity is from u to v. This time 0 to t and velocity u to v that we are considering here are the terms which are involved in the system. When these forces F1, F2, F3 have been acting in the system for a time of, let us say, t, for a time of t seconds starting from 0 initial condition to the time t, then let us say the velocity has been changed for the body from u to v. That is, initial velocity of the body we are considering it as u and final velocity as v. So now what we are doing, we are taking the summation of all these situations. So from 0 to t as the time we are considering and the velocities u to v, if we are going to integrate the above equation, then we are going to achieve integral here 0 to t and integral here u to v. So when we integrate this equation, we will be obtaining m into v, where it is from u to v. When you simplify this, you will be obtaining mv minus mu. Okay. So at last we have obtained the equation as integral 0 to t r dt is equal to mv minus mu. This is the impulse momentum equation. Here, this left hand side term, LHS term, integral 0 to t r dt is called as the impulse, where this is the product of force and time. The term integral 0 to t r dt is called impulse and the units are, force units is newtons and time unit is seconds. So the units would be Newton second. If R is constant, that means if all the forces that are acting in the system, here we have considered them as F1, F2 and F3. Let us say that all these three forces are constant throughout the time from 0 to t. Throughout the time from 0 to t where we are considering the system, then we can say that this R is a constant and the 0 to t time would be the complete time of the system and that is t. So we can replace or we can get the changed impulse term as R into t, where R would be the constant for throughout the time and t is the time from 0 to t. When you consider that, you will be getting the impulse term as R into t. Therefore, impulse is equal to final momentum minus initial momentum. Okay, nothing but impulse is equal to change in momentum. We can simply say that impulse is equal to change in momentum, where impulse is force into time. The product of force and time is called as the impulse and the final momentum minus initial momentum, that is change in momentum. We have already discussed that momentum is the product of mass and velocity. As velocity is a vector quantity, impulse is also a vector quantity. As per the given equation, this impulse will become a vector quantity as velocity term is involved in the system and the velocity is a vector quantity. Hence, the impulse term is also a vector quantity. We can directly say the force into time. That means force is a vector quantity, right? So, it could be the impulse would also be a vector quantity. Now, let us discuss about the topic conservation of momentum. Okay, The conservation of momentum, we can simply say it as the statement as momentum is conserved even before and after the action and reaction. Let us say there is an incident that is happening, uh, and that incident is being considered into two parts, beginning part and the end part. Then the momentum is said to be conserved when the both points or both parts are combinedly considered. That means momentum will not be changed. Complete consideration of the momentum initial to the final stage, the momentum is conserved. That means there is no change in the momentum. So before the incident and after the incident, the momentum would be equal. The momentum before the incident and after the incident will be considered as equal. So the statement is given like this. In a system, if the resultant force is equal to 0, the resultant which we have considered for a system, the resultant force R is equal to 0, then the impulse momentum equation reduces to mv is equal to mu. Right? How it has happened? R into T is equal to mv minus mu. That is the impulse momentum equation we do have. Now, when resultant is equal to 0, that means for a equilibrium condition system. In equilibrium condition system, or we can say in equilibrium system, the resultant would be 0, isn't it? So here we can consider that in an equilibrium system, when the equilibrium system is considered, the resultant would be 0. So if such a system is considered, if the resultant is 0, then what happens? 0 is equal to mv minus mu. This can be implied as mv is equal to mu. Okay, so with this we can say that it is the final momentum is equal to initial momentum. Okay, now we have achieved or we have ended with the result as final momentum is equal to initial momentum. So like this, if you consider when resultant is 0 in a system, then we can say that the initial momentum or final momentum is equal to initial momentum. Such situation arises in many cases because the force system consists of only action and reaction on the elements of the system. Okay, so because of the application of the force before the application and after the application, that are the two conditions or two parts that we will be able to consider. So before the application of the forces and after the application of the forces, what are the differences that are being happening in the system that are considered? The resultant force is 0 only when entire system is considered. Okay, as we have discussed, if we consider both the parts at a time, then only this conservation of momentum will be happening. How? Before the action and after the action. We can say action part and reaction part. Okay, when action part is happening, there would be some effects on the system, and when reaction part is happening, there would be some effects on the system. When the both action and reaction, that means before the application and after the application of the forces, all are combinedly considered, then only the system can be considered as in equilibrium state or the resultant is equal to 0. So, but not, we can say that, but not when the free body of each element of the system is considered. That means the resultant force is 0 only when entire system is considered, but not when the free body of each element is considered. Okay, so we have to consider all the objects or all the bodies that are present in the system, and we need to consider before the application of the forces or before the action and after the action. So both action and reaction parts should be considered, and all the bodies should be considered in the system. Then only we can say that the momentum is conserved. Okay, so the principle can be stated here as the momentum is conserved in a system in which resultant force is 0. Okay, the momentum is conserved in a system in which the resultant force is 0. When the resultant force would be 0? Resultant force would be 0 only when all the bodies are considered and before and after application of forces or before and after the action that is happening, two parts, both the parts are considered, then only we can say that the momentum is conserved. This is regarding the impulse momentum equation and the conservation of momentum. This concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.